Dear learners, so far we learned how to construct tables. Now we will learn how these tables are normalized, which is the theme of this unit. Introduction. This unit focuses on the splitting of complex tables into simple, meaningful tables. Objectives. The objectives of the unit are to understand the normalization process, why tables need normalization, functional dependencies in tables, first normal form, second normal form, and third normal form, how tables are normalized up to third normal form. Introduction to normalization. Dear learners, as you know that a database is an integrated collection of data, the large tables need meaningful subdivision into smaller tables. These small tables are easy to administer and control for efficient processing and storage. The normalization is the process by which a table is splitted into smaller meaningful tables. Dear learners, here an important question arises. Why a table needs normalization? The splitting of a table is evaluated in terms of three anomalies. These are insert, update, delete. Let us now discuss each in more detail. Insert anomaly. It is the problem of adding new row in a table for one or other reason. For example, consider table course as shown. The analysis of the table course shows that it is a valid table as it satisfies all basic conditions such as the table has a primary key which ensures that each row is unique and each column is unique. Dear learners, though it is a valid table, but let us see what will happen if it is required to add a row in order to define a course with course code CS3441 entitled Computer Networks with the assumption that this course is not registered by any student. This can be done only if providing values of primary key attribute that are registration number and course code, but the value of registration number is missing as the course is not yet registered by any student. Thus, course data cannot be defined unless registered by a student. Therefore, the course table has insert anomaly. Update anomaly. It is the problem of updating a row in a table for one or other reason. For example, in the table course, if it is required to update the course title, database 1, then it needs multiple updates due to redundancy. Thus, the course table has the update anomaly. Delete anomaly. It is the problem of deleting a row or rows from a table for one or other reason. For example, in the table course, if it is required to delete the course registration of student with registration number R3 for course CS3413 data communication, this will result in the deletion of entire row and will also delete the course data CS3413 and data communication. Thus, the table course has the delete anomaly. Dear learners, a table with any of the anomaly discussed is considered to be a poor table. Therefore, such tables need some treatment. The normalization is a technique used to control these anomalies discussed earlier. Dear learners, there are two stages of normalization. These are simple normal forms, higher normal forms. Most of the business applications need simple normal forms. Therefore, only simple normal forms are discussed here. Dr. E. F. Codd proposes the simple normal forms. There are three stages of simple normal form. These are first normal form, second normal form, and third normal form. Let us discuss each in more detail. First normal form. A table is said to be in first normal form if there is no multi-valued attribute. For example, consider the table student as shown. The sample rows show that each student has one value of name and phone number. Dear learner, the table student is in the first normal form because there is no multi-valued attribute. Let us modify a business rule for the table student as a student may have many phone numbers. The sample rows are shown as analyze the table carefully for validity. Do you think this is a valid table? Surely not, because It violates an important rule of database tables, that is, there must be primary key. The existence of multi-valued attribute phone prohibits the primary key definition. This problem is handled by two ways. These are: eliminate the multi-valued attribute by defining composite key as shown. Now the table shown as is a valid database table as there is a composite key. But this method of eliminating multi-valued attribute is not effective and has a serious drawback, that it introduces the update anomaly due to redundancy. For example, in the table as shown, the name of student, that is Arsalan, is stored redundantly. Let us discuss second solution of the stated problem. Extract multi-valued attributes from given table and place them in a separate table such that the newly created table must have a composite key. This composite key must have the primary key of original table as a part. This means that the original table, which is not in the first normal form, shall be decomposed into two tables, such that multi-valued attributes are placed in one table and single-valued attributes are placed in another table. Dear learners, a table with multi-valued attribute may also be converted into first normal form by replacing the multi-valued attribute with an atomic attribute for each value. For example, the table student with the multi-valued attribute phone as shown. It is converted into first normal form by replacing the multi-valued attribute with atomic attributes for a number of phone values as shown. This approach should be avoided for these reasons. If new phone number is required to be added for a given student, this may be done only by adding new column to the table. This brings structural changes in the table. Therefore, each time a new value is to be added, structural change of the table is required. It is not necessary that a given student must have defined number of phone numbers. Therefore, blank spaces may be stored against the phone number for which there is no value. This leads to storage wastage. Functional dependency. The functional dependency is the relationship between attributes of a table. It determines how the values of one attribute A determine the value of another attribute B in table T. Graphically, it is represented as shown. It is important to note that the attributes on either side of the arrow may be more than one as shown. The attributes at left side of the arrow are called determinant because it always determines the value of each attribute at right side of the arrow. For example, consider the table student as shown. Look carefully. The value of attribute name could be determined by knowing the value of attribute registration number. Similarly, knowing the registration number of a student, the value of attribute city could also be determined. This is shown graphically as. Dear learners, now it is time to discuss various types of functional dependency. These are partial dependency, full dependency, transitive dependency. In addition, there are other types also, which are beyond the scope of current discussion. Therefore, only stated dependencies are discussed here. Partial dependency. It is the dependency where non-key attributes are functionally dependent on any part of the composite key. For example, consider the table employee as shown. Dear learners, let us analyze the table. Knowing the value of key attribute employee ID, the value of non-key attribute name can be determined. Thus, the non-key attribute name is partially dependent on composite key. This dependency is represented graphically as shown. Similarly, knowing the value of key attribute software ID, the value of non-key attribute software title can be determined. Thus, the non-key attribute software title is partially dependent on composite key. This dependency is represented graphically as shown. Full dependency. It is the dependency where non-key attributes are functionally dependent on complete composite key. For example, consider the employee table once again and look carefully. The value of known key attribute hours worked can be determined only if knowing the values of all key attributes that are employee ID and software ID. Thus, the known key attribute hours worked is fully functionally dependent on composite key. This dependency is represented graphically as shown. Transitive dependency. It is the dependency where known key attributes become determinant of other known key attributes. Dear learners, look at this table carefully. The value of known key attribute date of completion could be determined by knowing the value of known key attribute project ID. Thus, the known key attribute project ID becomes determinant of another non-key attribute date completion. This is transitive dependency and is represented graphically as shown. Second normal form. A table is said to be in second normal form if it is in first normal form and there is no partial dependency. Dear learners, there are two possibilities for existence of partial dependency. Each one is treated in different way. These are along with full dependency, without full dependency. Let us discuss each in more detail. A table having partial dependency along with full dependency is decomposed as: convert each partial dependency into a new table. The determinant of each partial dependency becomes the primary key attribute of corresponding table. The full dependency is converted into another table. Dear learners, look at the employee table. Do you think the table is in the first normal form? Yes, very good. The table is in the first normal form because there is no multi-valued attribute. Let us evaluate the table for various anomalies. Here is the analysis. New software cannot be added until an employee is assigned to it. Similarly, new employee cannot be added until software is not assigned to that employee. Thus, we are forced to stop adding rows, so the table has insert anomaly. Multiple updates of a software title are needed as it is redundantly stored. Similarly, multiple updates of an employee name are also needed as it is redundantly stored. Thus, the table has update anomaly. By deleting the employee Fawad Rauf, the data of Visual Basic software is also deleted as there is single employee working with it. Thus, the table has delete anomaly. Dear learners, the table is in the first normal form, but still it has all anomalies. Let us find out the reason. Yes, there is a partial dependency along with full dependency. Now, let us find out the solution. The solution is that: first, identify the partial and full dependencies as shown. Then, apply the decomposition rule as: the partial dependency as shown is converted into employee table. The determinant of this partial dependency, that is attribute employee ID, becomes the primary key attribute of employee table. Similarly, the partial dependency as shown is converted into software table. The determinant of this partial dependency, that is attribute software ID, becomes the primary key attribute of software table. The full dependency as shown is converted into work table with composite key attributes that are employee ID and software ID. Dear learners, let us now compare the employee table before splitting as shown with the newly created tables, employee table as shown, software table as shown, and work table as shown. The new employee could be easily added in the newly created employee table, which is not possible without software in original employee table. The new software could be easily added in software table, which is not possible without an employee in original employee table. The software title update in software table does not need multiple updates as there is no redundancy, while need multiple updates in original employee table. Similarly, the employee name update in new employee table does not need multiple updates as there is no redundancy, while need multiple updates in original employee table. The employee deletion from new employee table has no effect on software table, while software data is deleted on deletion of an employee from original employee table. But an employee deletion from new employee table and software deletion from software table has effect on work table. This issue is controlled by applying integrity rules which are beyond the scope of current discussion. Dear learners, let us now discuss second possibility of existence of partial dependency, that is without full dependency. A table having partial dependency without full dependency is decomposed as each partial dependency is converted into a new table. The determinant of each partial dependency becomes the primary key attribute of corresponding table. The composite key attributes of original table are placed in another table with a composite key which comprises the primary key attribute of each new table. Consider the employee table with an assumption that a given job may be assigned to only one employee, but an employee may be assigned many jobs, as shown. Dear learners, the table is in the first normal form because there is no multi-valued attribute. Let us evaluate the table for various anomalies. Here is the analysis. New job cannot be defined until not assigned to an employee. Similarly, new employee cannot be defined until a job is assigned to that employee. Thus, we are forced to stop adding rows. Thus, the table has insert anomaly. The name update of an employee need multiple updates as it is stored redundantly. Thus, the table has update anomaly. If it is required to delete the employee named Daniel Daud, this leads to the deletion of job J3 data also. Thus, the table has delete anomaly. Dear learners, the table is in the first normal form but still has all anomalies. The only reason is the existence of partial dependency without full dependency. As discussed earlier, first identify the partial dependency as shown. Then apply the decomposition rule as the partial dependency is converted into a new employee table. The determinant of this partial dependency, that is attribute employee ID, becomes the primary key attribute of new employee table. Similarly, the partial dependency as shown converted into job table. The determinant of this partial dependency, that is attribute job ID, becomes the primary key attribute of job table. The composite key attributes of employee table before splitting, that are employee ID and job ID, are placed in employee job table as shown. Dear learners, let us now compare the original employee table before splitting as shown with newly created employee table as shown, job table as shown, and employee job table as shown. A new employee could be easily added in newly created employee table, which is not possible without job in original employee table. A new job could be easily added in job table, which is not possible without job in original employee table. An employee name update in new employee table does not need multiple updates as there is no redundancy, while need multiple updates in original employee table. Similarly, the update of job description in job table does not need multiple updates as there is no redundancy, while need multiple updates in original employee table. The employee deletion from newly created employee table has no effect on job table, while job data is deleted on deletion of an employee from original employee table. But the deletion of employee from new employee table and deletion of job from job table has effect on employee job table. This issue is controlled by applying integrity rules which are beyond the scope of current discussion. Third normal form. A table is said to be in third normal form if it is in second normal form and there is no transitive dependency. Dear learners, it is now clear that if a 2NF table has any of the insert, update or delete anomaly, then there is transitive dependency. The table is refined to 3NF by separating each transitive dependency and convert it into new tables. The determinant of each transitive dependency becomes primary key attribute of corresponding table. There are two possibilities for existence of transitive dependency. These are where the determinant has single attribute, where the determinant has multi-attribute. Let us discuss each in more detail. Single determinant attribute. If a 2NF table has a transitive dependency where the determinant has a single attribute, then the transitive dependency is converted into a new table. Dear learners, the transitive dependency is not restricted to one. Thus, each transitive dependency is extracted from original table and converted into a new table. The determinant of each transitive dependency becomes the primary key attribute of corresponding table. Add the primary key of each table resulted from transitive dependency as foreign key in original table along with all remaining attributes. Consider the table employee once again. As shown, look carefully at the table. Is the table in the first normal form? Yes, the table is in the first normal form because there is no multi-valued attribute. Now analyze it for second normal form. It is very easy as there is no composite key. Therefore, there is no chance for existence of partial dependency. Thus, the table is in the second normal form. But let us evaluate the table for various anomalies. New project cannot be defined until an employee is not assigned to the project. Thus, the table has insert anomaly. The update of project completion date need multiple updates because it is stored redundantly. Thus, the table has update anomaly. The deletion of an employee may result the deletion of project data also if there is single employee in that project. Thus, the table has delete anomaly. Dear learners, the table is in the second normal form but still has all anomalies. The only reason is the existence of transitive dependency as shown. Now let us resolve these anomalies. This second normal form table needs decomposition as the transitive dependency as shown is converted into project table. The determinant of this transitive dependency, that is attribute project ID, becomes the primary key attribute of project table. Add this primary key to employee table as a foreign key along with remaining attributes. Dear learners, let us now compare the employee table before splitting as shown with newly created employee table as shown and project table as shown. New project could be easily added in table project, which is not possible without an employee in original employee table. The update of project completion date in table project does not need multiple updates as there is no redundancy, while need multiple updates in original employee table. The deletion of employee from table employee has no effect on table project, while project data is deleted on deletion of an employee from original employee table. The deletion of project from table project has effect on table employee. This issue is controlled by applying integrity rules, which are beyond the scope of current discussion. Let us now discuss multi-attribute determinant in transitive dependency. Consider the table route as shown. It stores the distance in kilometers of different routes along with driver identification. Dear learners, the table is in the second normal form as there is no multi-valued attribute and no partial dependency, but still the table has these anomalies. New route cannot be defined until a driver is not assigned. Thus, the table has insert anomaly. Deletion of driver data may result the deletion of route. Thus, the table has delete anomaly. The reason of all these anomalies is the existence of transitive dependency, but this time the determinant is composed of multi-attributes that are origin and destination. The table route is to be refined to third normal form by adopting the same decomposition rule as discussed earlier. The transitive dependency, as shown, is converted into distance table. The determinant of this transitive dependency, that is attributes origin and destination, becomes the composite key attribute of distance table. Add this composite key to driver table as a foreign key along with remaining attributes. Dear learners, let us now compare the route table before splitting as shown with driver table as shown and distance table as shown. The new route, that is origin and destination, could be easily added in distance table without driver information, which is not possible in route table. The deletion of a driver from table driver has no effect on table distance while route data is deleted. If driver data is deleted from route table, the deletion of route from distance table has effect on driver table. This issue is controlled by applying integrity rules, which are beyond the scope of current discussion.
Dear learners, so far we learned how the database tables are derived from entity relationship model and convert them into normalized form. Introduction. This unit focuses on how tables are organized into a detailed blueprint called logical design. Afterwards, how a logical design is converted into a physical design. Objectives. The objectives of the unit are to explain design objectives of database design, phases of database design, which includes requirements collection and analysis, conceptual database design, selection of database product, logical database design, physical database design. Introduction to database design process. Dear learners, the design is one of the most crucial phase of the information system development. The database design is implemented by a database product such as Oracle and MS Access. Therefore, it must be perfect and technically sound. Thus, a poor database design will lead to a poor system development. Dear learners, let us define database design process. It is the designing of logical and physical structure of database tables to accommodate the information needs of users in an organization. Design objectives. The major goals of database design are satisfy the information needs of the specified users and applications, provide an easy-to-understand structuring of the information, support processing requirements and any performance objectives such as response time, processing time, and storage space. Design phase. Dear learners, the database design process is a composition of 5 sequential phases. These are requirements collection and analysis, conceptual database design, selection of database product, logical database design, physical database design. Requirements collection and analysis. The requirements collection and analysis is the originating point of a database design. One must know and carefully analyze the requirements collection and analysis for effective database design. The major activities during this phase are the identification of major application areas and user groups that will use the database system under study. Existing documents concerning the application are studied and analyzed. Study the present operating environment, if any. The requirements analysis is carried out by a team of experts with the active participation of customer and other stakeholder. The stakeholder are those who have significant impact on system under study. Therefore, joint application design methodology is used for refining initial system requirements. The requirement collection and analysis phase is normally a time-consuming but is crucial to the success of the information system. Conceptual database design. The goal of conceptual database design phase is to produce a conceptual schema for the database that is independent of a specific DBMS. It involves two parallel activities. These are conceptual schema design, transaction design. Let us discuss each in more detail. Conceptual schema design. It examines the data requirements resulting from requirements collection and analysis. It produces a conceptual schema. The conceptual schema design is a complete understanding of the database structure, semantic interrelationships, and constraints. Dear learners, after a detailed discussion on conceptual design schema, now it is time to discuss the transaction design activity of conceptual database design. Transaction design. The purpose of transaction design is to design the characteristics of known database transactions in a DBMS independent way. Usually, only some of the database transactions are known at design time, and after the database system is implemented, new transactions are continuously identified and implemented. However, the most important transactions are often known in advance of system implementation and should be specified at an early stage. Transactions usually can be grouped into three categories. Retrieval transactions, which are used to retrieve data for display on a screen or for production of a report. Update transactions, which are used to enter new data or to modify existing data in the database. Mixed transactions, which are used for more complex applications that do some retrieval and some update. Selection of database product. The selection of a database product for database development depends upon two important factors: technical, non-technical. Technical. The technical factors are concerned with the suitability of DBMS product with reference of technical issues such as storage structures, access paths support, interface, architectural options. Non-technical. The non-technical factors are concerned with the suitability of DBMS product with reference of non-technical issues such as finance, support of the supplier. However, there are economic and organizational factors also that affect the choice of DBMS. These are economic factors, organizational factors. Economic factors. The economic factors are software acquisition cost. The software acquisition cost includes selected version of DBMS product, other software needed. Maintenance cost. This is the recurring cost of receiving standard maintenance from vendor and for keeping the DBMS version up to date. Hardware. The hardware cost includes new hardware needed such as additional memory, computers, disk drives. Database creation and conversion cost. This is the cost of either creating the database system from scratch or converting an existing system to the new DBMS software. This cost is hard to project and is often underestimated. Personnel cost. Acquisition of DBMS software for the first time by an organization is often accompanied by a reorganization of the data processing department. Positions of DBA and staff exist in most companies that have adopted DBMSs. Training cost. The DBMSs are often complex systems and the related personnel must often be trained to use and program the DBMS. Training is required at all levels including programming, application development and database administration. Operating cost. The cost of continued operation of the database system is typically not worked into an evaluation of alternatives because it is incurred regardless of the DBMS selected. Organizational factors. The organizational factors are organization-wide adoption of a certain philosophy. This is often a dominant factor affecting the acceptability of a certain data, a certain vendor, or a certain development methodology and tools. Familiarity of personnel with the system. If the programming personnel within the organization are familiar with a particular DBMS, it may be favored to reduce training cost and learning time. Availability of vendor services. The availability of vendor assistance in solving problems with the system is important since moving from a non-DBMS to a DBMS environment is generally a major undertaking and requires much vendor assistance at the start. DBMS portability. Many commercial database management systems now have versions that run on many hardware and software configurations. The need of applications for backup, recovery, performance, integrity and security must also be considered. Many database management systems are currently being designed as total solutions to the information processing and information resource management needs within organizations. Logical database design. The logical database design is the process of designing tables and their relationships. This database design is free of any DBMS product and could be easily implemented on any selected database product in lateral stage of design. The logical database design can be achieved by designing tables directly from the detailed description of the system under study without using any modeling tool such as entity relationship model. But it is strongly recommended that entity relationship model shall be used as structured analytical tool which is easily converted into logical database design. Physical database design. Physical database design is the process of choosing specific storage structures and access paths for the database files to achieve good performance for the various database applications. Each DBMS offers a variety of options for file organization and access paths. These usually include various types of indexing, clustering of related records on disk blocks, linking related records via pointers, and various types of hashing. Once a specific DBMS is chosen, the physical database design process is restricted to choosing the most appropriate structures for the database files from among the options offered by that DBMS. These criteria are often used to guide the choice of physical database design options. Response time. This is the elapsed time between submitting a database transaction for execution and receiving a response. Response time is also influenced by factors not under DBMS control, such as system load, operating system scheduling, or communication delays. Space utilization. This is the amount of storage space used by the database files and their access path structures on disk, including indexes and other access paths. Transaction throughput. This is the average number of transactions that can be processed per minute. Transaction throughput must be measured under peak conditions on the system. Performance depends on record size and number of records in the file. Hence, we must estimate these parameters for each file. Estimates of file growth either in the record size because of new attributes or in the number of records should also be taken into account during physical database design.